Hi, good morning, Matrix. This morning we're once again looking at work, energy, and power. And I just want to remind you that you can send us any questions that you have. You can send us questions to junior.tukkie@up.ac.za. Any of your questions. We're doing maths and physical science in the Junior Tukkie Winter School, and you can send us any of your questions. We've got a team of students who would love to help you, and also some of your questions might end up in a discussion like this. Right, the first question today we are going to do is one that is sent in by Japan. It says, Mr. John, a cyclist, rides a bicycle and he rides his bicycle at 10 meters per second. Now, guys, when you start off with a question, immediately start doing a drawing. There's a nice one, but let's do our own. The reason for a drawing is threefold. Firstly, when you read this, if you read while you're making the drawing, it will help you to interpret the situation. You will understand it better because you're not just reading, you are reading to make a drawing. Immediately, you will interpret and understand better. And then the second thing is, if it's a whole paragraph like this, once you've captured all the information on a diagram, you won't have to go back and reread the paragraph, which will save you a lot of time. And the third thing is, especially if you've got information in there, like say for instance 1.2 and 8 meters, if afterwards you are in a hurry and you just go back to get that distance, you might take the wrong one. Well, if it's on a diagram, then you will immediately know which one is which one, and you won't be tempted that much to take the wrong one. Okay, so first off, let's read 10 meters per second on a horizontal surface, and then he freewheeled on an inclined plane. Right, inclined plane of 8 meters long and 1.2 meters high. Right. Now, you don't have to have the correct ratios. It's just information, right? While freewheeling. Now, once again, he's telling you freewheeling. Now, what does freewheel indicate? It means he's not pedaling, right? So there's no forward force exerted by that boy. He's just traveling. Right, but as he's freewheeling, right, while freewheeling the incline, he experienced a frictional force of 8 newtons. So over there's a frictional force, and that's always in the reverse reaction, in the backward reaction, and that is 8 newtons. And then it says the mass of Mr. John and his bike is 55 kilograms. 55 kilograms. And at that moment, all the information up there is captured here. I don't need to come back. Now, the first question there is, will Mr. John maintain his mechanical energy whilst riding the inclined plane from A to B? Now, what does that word maintain imply? Maintain means it keeps it, right? It doesn't change. And in science, we use the word conserve, right? So they're actually asking you, is mechanical energy conserved? Now, to think about that, you've heard that word conservation of mechanical energy. You know, and I'm working from the exam guidelines with the absolute correct wording. Remember to always go back, right? The principle of conservation of mechanical energy is that the total mechanical energy in an isolated system remains constant, right? Now, in physics, an isolated system is just one where the net or resultant external force, and that is very important. There's no force working from outside on the system, right? Now, an outside force, that can be an applied force. That would have been if he had been pedaling, right? And he's not pedaling, right? And it can also be if there's friction. So remember that one refers to, and something work on the system from outside. Now, definitely here they're asking, will his mechanical energy be contained? And the answer is a definite no, because we've got friction, right? So the first question is definitely no, it will not be conserved. You have frictional force, friction, right? And that is a net or a resultant external force. Right, so a frictional, which is a non-external force, is working or acting on them. Right, and this implies it is not an isolated system. If it is not an isolated system, then mechanical energy is not conserved. So the friction is going to remove energy, some of the mechanical energy from the system. And that's why it's not a conservative force, right? It is taking energy and it is taking it out of the system. If you've got friction, you've got heat, right? And that heat is just dissipating into the surrounding area. Right, so that was the first question. Next up, they ask us to draw a free body diagram. Remember, free body diagram is free of a body. It is just a diagram of the forces. So you use a dot, right? It's free of a body. Don't go drawing something, eh? Just a free body diagram. Now, very important, we are on an inclined plane. So don't go and turn your forces horizontal, right? Keep the forces on an inclined plane. So what's happening over here? We've always got gravity, and remember, gravity is just straight down. Now for gravity, I like to use Fg, but we have to be very careful. We have to use the correct symbols that the Department of Education expect us to use. Otherwise, we have to say, to have a key to say this, for this, you can call it X. But X, then I have to say, okay, X represents the gravitational force. But if you use the correct label, and then you don't have to explain what the label means. Now, what is the correct label? Now, if you go to your exam guidelines, there's a whole table where they tell you what is the correct one. They actually tell you what they prefer, but what they will also take. Right, so actually for weight, they prefer a small w for weight, but they will also take Fg, right? So I can use Fg, or I could have used the W, right? Either one of those will be all right. Okay, so I've got that one. What next? Well, if it's on a surface, always perpendicular to that surface, you will have a normal force. Right, so the normal force. And remember to keep them, hey? On this force. Don't go turning them horizontally, right? And then what else? We've got a frictional force, and the frictional force is in the backward direction. So there you've got friction, and it's kinetic, so I'm just going to add that. Now let's just check the labels, right? For normal force, yes, N is accepted. You could also have used F with a sub N. And for friction, they prefer that small f, but they will also take f with a small f next to it. Right, so all of those were fine, or you could have used Fn, that was also all right. And friction, they prefer that one. Okay, or you could also have used F with friction, right? That would also have been all right. So you've got three possibilities, other possibilities, but use the correct labels. Okay, so that was the free body diagram. Next up, calculate the kinetic energy of Mr. John at position A. So over here, we are asked to calculate the kinetic energy. Now, don't start off by trying the most difficult things first, right? If they just ask kinetic energy, I'm first going to see, can't I just do a plain calculation? Okay, so I go to my table of information, and there you have for kinetic energy. And once again, can you see there's two different symbols that's both accepted, right? They are both accepted, and you can use either one. So that's just half mv squared. And what do we know about Mr. John and his bicycle, right? Let's think. EK equals half mv squared. We know the mass, right? That's 55. So this is just a half times 55. And we also know the velocity, 10 squared. So that was easy. That was just substituting. So don't go thinking it must be something big. Try the most plain one possible. So that will give you 2750 joule. Right, so that was question 3. Let's move on to question 4. Now for question 4, they ask us to calculate now the kinetic energy up there. So obviously now I have to work with this movement, right? Now if I look at this, I have to decide which equation to use. Right. Now remember, when you want to choose equations, you have to choose between different ones. You have to choose between conservation of mechanical energy, work energy principle. You've got the conservation of momentum. You've got the impulse momentum one. What is the most important thing? The most important thing is looking for a closed system or not, right? The moment you have a closed system, and in physics, you can also call that an isolated system. In chemistry, closed and isolated refers to different things, right? If you're doing chemistry, right, and you talk about closed, right, closed means no particles will escape, right? No particles will escape from your beaker or whatever, right? No particles escape. So if you're working with a gas, you need something that is closed at the top so that no particles can escape. That will make it closed, right? But isolated in chemistry refers to something where no particles and no energy, right? And no energy can escape or be absorbed, right? It's isolated from the surroundings. But in physics, we're using them any which way you like, right? But what is a closed system? No friction, right? And no applied force, right? Nothing working from outside and taking or adding energy, right? Friction would be taking out energy. Applied force would be adding energy. So the moment you have friction or an applied force, it is not a closed system and you can't use conservation of anything, right? But if there's friction, you have to work with either the work energy or the impulse momentum principle, right? Now in this one, we are going to use the work energy principle. But with work energy, you've got two different ones. If you look at the table, you will see there you can either work with the work energy, right? W net, right? The net work equal to kinetic energy, or you can change that and use what we call the non-conservative one, right? Now, when do I use the non-conservative force? Non-conservative is when you've got all the work done by all the forces except gravity. So I will use this one when gravity is a problem, right? When I don't have the angle, and sometimes I just say NC, it stands for non-conservative forces, but I just remember it's when I've got no corner, right? So the moment you have no corner, no angle down there, then the non-conservative force one will be the easier one. So for this one, I will prefer to work with the work done by the non-conservative forces. So then I don't have to worry about gravity. So now gravity is my conservative force. I only have to worry about the other two, right? Now, what do you know about normal force? Now, the movement is definitely up the plane, so that is the direction of movement. So your normal force is perpendicular to the movement. And remember, the work done by anything that is perpendicular is zero. So you can write down the work done by normal plus the work done by friction, but that one is zero, so you don't have to show it. Remember, for the department, when they mark, you don't have to show those because they are zero, right? But you can write it there. I like to write it because I want to make sure that I've done all the forces, right? So I'm working with the work done by non-conservative, so it's actually just the work done by friction. And that is equal, right? If it's the non-conservative, that is equal to change in EK plus change in potential energy, right? So I've got that, and that will be, now let's think about the kinetic energy. Change in anything is always the final value minus the initial value, right? Now, what do we know? Final value, that's what we're looking for, right? And the initial value we've already calculated. So I'm not going to substitute half mv square in here. I've already worked it out, right? But then we get to potential energy. Change in potential energy, that will be EP final minus EP initial, right? Okay, let's go substituting. We're working with the frictional force, right? Now, what do I know? Every work done is the force times the displacement times cos of the angle. So if I'm replacing friction, I'm going to say the force I'm working with is friction. The displacement, it is doing that, right? So the displacement will be 8, right? But let's just write that first, cos theta equal to, and then let's go and replace. That frictional force is 8, the displacement 8, and now how about the angle? Now look at the frictional force. The frictional force is downwards. What is the angle between that frictional force and the direction of movement? Right, you have to turn it 180 degrees to get to the direction of movement. So that is 180. And remember, cos of 180 is just minus. So this ends up being minus 64. Right, moving on to the right side. Kinetic final, that is actually what I'm looking for. So I'm going to leave it there. Kinetic initially, I've already calculated that, minus 2750 plus. Now, when I get to potential energy, mgh, now m and g will be in both of them, so I don't worry about them. I'll just take it out, put it in front, but that will be h final minus h initial, right? So here I have the kinetic energy final I'm looking for, minus 2750 plus, right, mass 55. G, now G, the gravitational acceleration. Now, whenever you're doing projectile motion, you need to know if that is plus or minus. But if it's an energy, then it's always just the magnitude, right? You put in just 9,8. So this doesn't matter what the directions are, right? Okay, 9,8. And then what is the final height? The final height is 1.2, and the initial height was 0. Right, I'm measuring from the ground. Right, so this is just EK final minus 2750, and then you can work that out. It gives you 646,80. Right, and now we just have to solve for the kinetic energy. Right, so the kinetic final, and that works out something like 2039,20. Remember to have 2 places after the comma. Right. Okay, guys, so that was the first question sent in by Chapang. Now we're moving on. The next question we're going to look at is question 40 over here. Right, I think someone needs our help. Now let's talk about this. A loaded bucket travels up a slope as indicated. Now let's do our own drawing, right? It's traveling up a slope as indicated. The total mass of the bucket and the load, okay, so you've got something and it is 1750 kilograms, right? It's driven at a constant velocity. Now, immediately there's going to be a problem, right? You can't work with anything that is kilometers per hour. So let's just quickly convert that. Now, if it's 72 kilometers per hour, it means 72 kilometers in 1 hour. And now I want to end up with that in meters per second. So let's take the 72. What do I have to do to the 72 to go from kilometers to meters? I have to multiply with 1,000 to get to meters, right? What do I have to do to 1 hour to get the number of seconds? Now, first, I will multiply by 60. That will take me to minutes. And then once again, with 60 to get to seconds, right? And all of that is just the same as dividing by 3,6 to get the meters per second, right? And that ends up being 20 meters per second. So that is the very first thing to do. Convert to meters per second because we can't use the kilometers per hour. Right. Now, it is a constant velocity. Now, guys, you can't stress that enough. If you've got a question and there's the word constant, just go and highlight it or underline it to remind yourself. This is very important because it's different, right? Yeah. It will tell you you're working with Newton's first law, right? You're working in a situation where there's no net force. Now let's move on. It's moving at a constant velocity up, so it is moving up at, and now I know it's moving up at 20 meters per second, right? And they tell us it travels 570 meters, and they tell us the top of that slope is 55 meters above the ground. Right, so I've read everything up to here and I've handled it. Right, moving on. The work done, now this is the first question. The work done against friction is 5,84 times 10 to the 6. Calculate the average power. Right, so we're looking at power. Right, output of the engine given to in kilowatt. Right, now if I have work done against friction, now I don't really like that, against friction, but it means that there's friction, and the friction has got that much energy, and now it must either put in or take out. Now what does friction do? Friction will always be in the opposite direction. It will always be minus 180 degrees, right? And that will always end up being, the work done by friction will be a negative, right? 5,84 times 10 to the 6. So this is very important. Friction will always do negative work on the object, right? Now calculate the average power. Now let's think, for power, what equations do we have for power? Now let's go and see, what equations do we have for power? For power, you have two different equations, right? You've got P equals W over delta T, all right? The work done divided by time, or you can use P average equals F times V average, right? Now, this one works for all situations, but the department tell you in the exam guidelines, they want to use this one only for constant speed. So keep this one for constant speed, right? But at this very moment, we are moving at constant speed. So it's actually, there's two possibilities. We can work with either one, right? Now, let's go and see what we can do over here. We need the work done, and it is definitely the work done by the applied force. So what's the first thing to do? To go and draw a diagram, right, of the free body diagram for all the forces. You've got friction, and now say calculate the average power output of the engine. So obviously the engine is pushing forward, right? So let's think about the forces. You've got your engine, right? You've got the applied force of the engine pushing up. You've got your friction working down. There's always gravity working straight down, and there's always your normal force, because you're on a surface, you've got the normal force perpendicular to that surface, right? So we've got four forces over there. And once again, like in the previous question, I don't have the bottom angle, right? If I've got no corner, then I know the easiest way to do this would be to work with the non-conservative forces, right? And what does non-conservative force mean? Everything except gravity. Hey, gravity is my conservative force, right? If it's a conservative force, I'm going to ignore that when I work with non-conservative. Right, so this is actually the work done by that normal force plus the work done by the applied force plus the work done by the frictional force. Right, and that is equal to change in kinetic plus change in potential. Right, now, remember the normal force is perpendicular to, so that normal force will be a 0, and you don't have to show it. Strictly, you can leave that out, right? So, if you look at this one, next up we have the work done by the applied force. Now that is actually what we are looking for, because we need to work towards the power of that engine, right? The power of that engine. So the work or the force, this is what we need. So not going to replace that one. We're going to leave that one. Right, and now we get to friction. Now, what do we know about friction? We know the whole work done by friction, right? The whole work done by friction, don't know where I wrote that down, is negative 5,84 times 10 to the 6, right? Minus, because it's removing energy from the system, right? Now, what is change in kinetic energy, right? It is the kinetic energy before minus the kinetic energy afterwards. And now we get to something. Remember, the velocity is constant. Right. And if you look at your kinetic energy, that is half mv squared. If the velocity is constant, it means my kinetic energy is constant. It's staying the same. It's not changing. So what is my change in kinetic energy? It is not changing. So that one will be a 0. If I'm traveling at constant velocity, my kinetic energy is not changing. Right. And then we get to m, g, and h final minus h initial. Right. Mass, they gave us 1750. G, remember we were doing energy, so I'm not putting a plus or minus with that 9,8. Final height, now it's going up the slope, so the final is 55 and the initial was 0. Right. And then it's just a question of working it out. What is the work done by that engine applying the force? And you end up with something like 6,78 times 10 to the 6, and energy is in joules. Right. So we've gone up to this part. We've got the work done. Now I have two different equations that I'm working towards, right? I've got the one that I want to work towards is the one where we are going to work with P equals V, F times V, average, right? That is one that we can do. The other one is P equals W over delta T. Now, immediately, if you are going to use that one, we've already got the work done, right? We have the work done by that engine, and that is 6,78 times 10 to the 6. So over here, the problem would be to get the time, right? Now, to get the time is not that difficult because you have the velocity everywhere because it's 20, right? And you also have the distance. You have the delta x over there. Right. Now, for this one, I would like to use an equation of motion, and there is more than one that you can use, but let's start by saying delta x equals v initial delta t plus a half a delta t squared, right? The distance traveled will be 570. The initial velocity is 20, right? And we are looking for the time, and what do we know? It's traveling at a constant 20, so it is not changing velocity, so it is not accelerating, right? So that is 0. Now guys, I know you like to say delta x v equals delta x over delta t, right? This is only true. You can see it over here. V is delta x divided by delta t. This is only true when something is not accelerating, right? So I would prefer to use with this one and to show them that I know that a is 0, but you can do that. Just write down the reason why you're using that, right? If you are accelerating, then that one is not true. Okay, and then you have to solve for delta t, and you get something like 28,20 seconds, and then I can add it there, 20,20 to get 2,38 times 10 to the 5 watt, right? And in the question they said we have to do that in kilowatt, right? Now what is kilo? Kilo is 10 to the third, right? Now how do I get to 10 to the third? I take 100 of that and already multiply that in there, so that's 238 times 10 to the 3, right? I've used 100 of that already to multiply, right? And that means I end up with 238 kilowatt. Right. Okay, so let's try the other way around. Now, the other way around, we are working towards F because we need that. We've got already the V, right? It's traveling at 20 meters per second, right? So what do we need to do? We need to convert or to go from the work done by the force to the force itself, right? So the work done by that force is F delta x cos theta, right? And I know it's 6,78 times 10 to the 6. I'm looking for the force, right? What is the displacement? Now the displacement over here is that 570 meters, right? So it's 570, and then I want the angle. I'm working with F. What do you know about the F? F is in the direction of movement, right? So that angle will be cos of 0. right? And then you solve for F, and you get something like 1189,47 Newton, right? Don't worry if you've got a little bit of a rounding difference, right? They mark a range, right? They actually prefer that you keep everything inside your calculator. Don't round off every step, right? Keep everything inside and then just round on the very last one. But they mark a range, so don't worry too much about this. Just try to get it more or less the same for 7, right? And then the velocity was 20. And if you do that, you once again end up with 2,38 times 10 to the 5 watt. And same as here, that will be 238 kilowatt, right? So we are now finished with the first one. We've calculated the average power. Now, what was the net force on the bakkie at a point halfway up the slope? Now, it doesn't matter how far you are up. What do we know? We know that it is traveling at a constant velocity, right? And if it's traveling at a constant velocity, I am immediately working with Newton's first law that tells me an object will remain in its state of rest or traveling at constant velocity except if there's a net force. So that tells me that the net force at that moment is 0, right? 0 newtons. There's no net force working on that according to Newton's first law. Right. Moving on to the last part of this question. The bakkie is emptied of its load, and the empty bakkie, now stop the bus. The moment that they do this, they are changing the whole thing. So be very careful. Go and make a new drawing, make a new force diagram. Don't expect that anything is still the same as when you were going up the slope, right? So we are actually starting a whole new question, right? So don't go assuming anything, right? So what do we know? What is going to stay the same? Well, obviously it's the same slope, right? So that 570 and that 55 meters, that will still be the same, right? Now, they've emptied it, and now the mass is just 1100 kilograms, and now it's traveling down the slope, and it accelerates. So immediately I'm not working with Newton's first law, I'm now working with Newton's second law, right? And it's traveling, and it's starting at the 72 over there. Remember, we've already converted that to 20 meters per second. Right, and it's going down here to 90. So the second thing will be, let's quickly go and convert that 90 kilometers per hour. What do? I divide by 3.6, the same way as before. And if I divide that by 3.6, let me just find my calculator. Right, if I divide by 3.6, I end up with 25 meters per second. Right, so we've got 20 up there, and then we've got a 25 meters per second down there. Right, now they tell us the average frictional force. So they're giving us the frictional force now. The frictional force is equal to 6,44 times 10 to the third Newton. And now they ask, how much work is done by the engine? Okay, so the engine is still working while the bakkie is accelerating. Right, now let's start with a new force diagram. Right, we've on the same Earth, so our gravity is still down. We're on the same surface, so we've still got our normal force up there. Right, but now it's traveling down, so the engine, the applied force is down, and the frictional force is in the upward direction because it's always in the opposite direction of movement. So we've got a whole new set of forces, right? And now they're asking how much work is done while the bakkie is accelerating. Now there's friction, so obviously no conservative forces, conservation of mechanical energy or something. We really need to work with all the forces, right? Now, once again, they don't give us the bottom angle, so let's work with the work done by the non-conservative no corner, right? Delta EK plus delta EP. Now, Gravity is my conservative one, so that is not being used with non-conservative. With non-conservative, we have the work done by the normal force, plus the work done by that applied force, plus the work done by the frictional force. And that gives you change in kinetic will be half m v final squared minus v initial squared. And change in MP is potential energy is mg h final minus h initial. Right, let's go replacing. Now remember normal force perpendicular to the movement once again, right? So that is 0, and you don't really have to show it. You may leave that out if you want to. Right, we're looking at the work done by the applied force. Now that is what was the question, right? How much work is done by the engine? So we want that work done by the applied force. So that is the unknown, right? Now, next, we're moving on to friction. Now, this time they didn't give us the work done by friction. They gave us the force. So it's 6,44 times 10 to the 3 times the distance. It's moving 570 times cos. And now, friction is up and the movement is down. So you've got an angle of 180 there between them, right? An angle of 180. And that will be equal to, and now we're starting to substitute the right-hand side, that will be equal to half mass. Now they've given us this new mass, 1100, and the final velocity, it's down there, that was 25 squared, minus the initial velocity up there, that was 20 squared, plus mass 1100 g. I'm working with energy, so it's not plus or minus, it is just 9,8, right? Final height, now it's ending up at the bottom, right? So don't go switching it around. This final height is now 0 and the initial height was 55. So there you've got everything, and you just need to solve for the work done by that engine, that applied force. And if you work that out, I hope you work with 3,20 times 10 to the 6 joule. Right, more or less. Right, remember you can have a little bit of rounding because you're going to do this in different ways on your calculator. But remember you need to have 2 digits after the comma. Right, guys, next up, I just want to look quickly at one question that was sent that is actually not a question on work, energy, and power, right? There's just one question, and I don't want to look at everything. It's actually a question with projectile motion, and I just want to look at one thing. They say a learner throws a book vertically downwards from a window on the top floor of a school building at a velocity of 5. Immediately drawing, right? So it's throwing it down at 5 meters per second, and it hits the ground after 3 seconds. And then the first thing was not a problem for this guy. He said, calculate the velocity at which the book hits the ground. So that was easy. We were looking for V final, right? We had V initial over there, and we had delta t. If you're working with downwards, it means V initial is a plus 5 meters per second. V final is what we are looking for. G, well, if you choose down, remember gravity is down, then it is plus 9,8 because the gravitational acceleration is in the direction of movement. And delta t given as 3 seconds. So that is just find the correct equation of motion and substitute. The problem was for this guy was the distance the book drops during the second, right? The second. Now that is what we are talking about. Now let's say we're starting out at time 0, right? Then we have after 1 second, and then we have after 2 seconds. So if they're talking about that part, they're talking about the first second, right? If they're talking about that part, they're talking about the second. So they are actually looking for that distance. So first you are going to work out the distance up to there, right? So you're going to work out the delta y for 2 seconds, right? And then you are going to work out the delta y for up to there, the delta y for 1 second. So there you substitute 2 seconds, there you substitute 1 second, and then for the delta y in the second, you will have to take the whole distance traveled in 2 seconds, right? And subtract from that the distance traveled in 1 second. So I'm not going to do that since we're looking at work, energy, and power. I just want to show that guy how to interpret the word second. Right, guys? Next up, we're going to look at acids and bases this week. And next week, the discussion will be on your questions for acids and bases. Just remember to send us your questions at junior.tukkie@up.ac.za. Right, guys, have a wonderful week.